Good. So the plan for today is going through the second part of the process in a model-free situation, which is the control. So I'll review the last lecture. So I'm going to review the last lecture where we learned to deal with the model-free situation where you do not know the underlying MDP. So the world is working stochastically, you just don't know the transition probability. You don't know what the world will give you as reward a priori till you go and experience it, right? So there is a Markov process. You go somewhere, you go to a market and you decide to buy something or not. You go to university, you go to a bar, whatever, and there are certain consequences that happen. You are not aware of it beforehand, what will happen, but you can experience it. The model-free way of doing things is go, have the experience, collect the reward, good or bad, and then evaluate your strategy. Right? It's basically the principles. The first part is what we did, evaluate your strategy. So that's what we did last time. Second part we'll do is, okay, can I improve my strategy? So now that I have evaluated the strategy, can I improve the strategy? Can I improve the policy, as the jargon is? But in real life terms, in a very philosophical term, you go through your experience of life, you whatever, eat, sleep, learn, play, and whatever works for you, you evaluate whether it is working for you, what is not working for you, and you try to improve it. This is the plan. So what was it that we saw? We saw two, so of course, we saw basically two extreme cases and then everything in between. The two extreme cases of how we can evaluate. One is the Monte Carlo way of doing things, where you first go through an entire chain of experiences till you come to a terminal state. So this is more applicable in games or in other kind of problems where there is a finite horizon. Finite horizon is when the episode is finite. So in all kinds of games, all kinds of other simulatory problems where you can end somewhere, Monte Carlo is a good thing. You can sample a whole episode from some state to the very final state, whether you have lost the game or won the game, for example, or drawn the game, blackjack. You take a whole episode, collect all your reward, and use that information to update your estimate of how good your policy is. So you judge your policy by going through the whole thing. The advantage, of course, is that there is no bias because you're going through to the end. It's not biased, but it has so many probabilities at every step. You're including randomness, so there is a lot of variance in it. So this was one extreme of how to evaluate your policy. The other extreme was the temporal difference method. So this extreme, again, going back to Monte Carlo, this works when we can have the whole episode, right? You cannot do Monte Carlo to your life. You cannot go back to your death and then come back and say, no, that's what I did wrong in my life. It happens only in movies. But you can do this TD, a temporal difference thing, where you experience one event, one action, one transition, and try to update the value of your policy. So from that, you want to learn the value function of the state. Right. So this is what we did last time. So this tells us, by now we know how to compute our value function. Okay. And what is the next thing? So once you have an estimate for how good or bad your current strategy is, you want to do the second thing. So first you have a policy, a current strategy, you evaluate, you get some function, the state value function or the action value function, and now your job is to improve it and create a new policy, right? Once you have created a new policy, you evaluate the new policy, and you go round and round till you get the optimal policy. This is usually the plan. So to evaluate, you need Monte Carlo or TD. But to improve, we already know one method of improving. What was the method we saw already? It's the greedy method. Take the best action that your policy is telling you to take. That's the method we know, the greedy method. So evaluate all the actions, and take the action that is best you think at this time, right? And then that's one mechanism. We will learn the other mechanisms today. The epsilon greedy. I might or may not talk about the Boltzmann. I think I've listed it, but we'll see. Okay. So this is what you do. Now this is the plan. Okay. Did I go back or forward? I went forward, right? Good. So what we learned last time was to compute the value function. What we learned last time was compute the value function by either Monte Carlo or TD or TD lambda, right? But if you only know the value function and you want to compute, say, using the greedy algorithm, the greedy thing, the new policy, you still need the model, because this is the Bellman equation. Long time ago, we talked about the Bellman equation, but I'm sure this has been repeated so many times that you're aware of it by now. Okay, so to improve your policy with the greedy algorithm, if you just had the value function, you would need to know the reward and the transition probabilities, the P matrix for every action. But what are we assuming? We are assuming that we don't know this. Nobody has given this. Is hidden from us. This is what we are unaware of. Hidden information. So the other way is, so what is the other way? What should you do? What is a guess? Any idea? So in fact, if this formulation requires you to know the value function, what should you do to avoid getting all of this information a priori? Oh, that's what we're doing. So we did the evaluation process and we have somehow approximated the value function. So we got the value function, all right. But to apply this greedy strategy to get pi prime, we need the value function, which we have, say, obtained by TD or Monte Carlo. But we also need in this equation the probability matrix, right? So instead of computing the value function, just the state value function, one should consider computing the action value function. Right? So you could rewrite that in terms of the action value function, okay, the Q function, and that also works. But now you will have to do something more. Now you'll have to compute QSA by Monte Carlo or by TD. So instead of saying I am going to compute the value from a state, I am going to start in a state, take an action, and then compute the value. Okay. So what should the Monte Carlo consist of? You start in a state, take an action, then take the whole episode, then update the value of the state action. In the TD also, you start in a state, take your action, then experience one more action. Right? This was forced on you. You were in the state as, you took one action, then you take an experience with your policy and then evaluate it to change. We'll see the exact formulas. I'm just saying, just talking one time, so that repetition is a good thing, right? On more you repeat, easier it is to understand. So what we are now interested in is the Q function, and which we can work out more or less by the same strategy. You can evaluate it more or less by the same strategy. Right? So this is what you would have done if you would use the greedy algorithm to improve your policy, as we did in the dynamic programming. Okay, but there is in red a warning written here. And the warning says that the greedy algorithm does not explore. What does that mean? I'm going to. Oh, sorry. So now remember, we don't have all the information about your model. So you are in a state as, you take action 1, maybe you take action 2, okay, and you observe here a high reward, you observe here a low reward. What will the greedy do? Will take the one with the high reward. Previously, what you did is you just did not just consider the observation, you knew the probability here. So what can happen is you start with this state and you go A1, and here there is, you can get to whatever, S1, S2, whatever. Low probability, medium reward, high probability, medium reward. Okay. And you go with the second action, low probability, low reward, high probability, high reward. So if this is your situation, which action would you like to take? So in this case, you will always get a medium reward, and there with low probability, you'll get low reward, with high probability, you'll get high reward. Which one would you take? You take this one. But what can happen when you experience it only one time, that you can get the low probability information here. Because experience is an experience. It's not information about how likely something is. So what can happen is you get this low information here, although this is not the reality. The reality is that, in fact, it's rare that this is the risk, of course, that you can get low, but this is a low chance of getting low here. It's a high chance of getting more here. Right? So this is the more optimal action, and you don't discover it if you just take greedy policy in a model-free world. When you had the model, when we did the dynamical programming, we actually put in the probabilities here, and that is why the greedy algorithm was working. If you go back and check the dynamical programming greedy algorithm statement, then you will see that you're not choosing any action, but you're also weighting the actions by the probability times the reward. Right? That's what we mean by the best action. Okay. So in experience, you cannot find this probability. We don't know what the probability is, and the greedy algorithm will get stuck. It thinks, it goes this side and says, oh, this gets me good, then it will always stick to this side. So this brings up the most important question in model-free reinforcement learning. And that is that Since you don't know the probabilities, your experience can, in one experience you might be lucky and you get a lot of reward, which is a rare event. You might be unlucky. You might not get the reward that usually should happen there. How are you going to judge anything? What is the way to judge things? Any guesses? What should one do in such a situation? We don't know the probabilities. What should one do? So in real life, you go somewhere and you had a bad experience. You go somewhere else, you had a good experience. Should you never go to the place where you had bad experience? Sorry, could you say that again?
Well, for going I have bad experience. Let someone else go there and then listen to their experience.
We will also do that. That's a good point. We will do that.
The same as you with the review, right?
Exactly. That, we will come to that. That will be the last thing we will talk about today. By the way, there is an official name for what you're saying. It's called off policy or off policy learning, which is learning from someone else, right? But let's just say we want to learn from our own experience. We live in a pre-internet world where we cannot read too many reviews about things or whatever. We don't have internet access. So what are we going to do? We want to try to explore things. Right? You want to try more and more things over and over again till you think you have found the optimal choice. Right? So what the greedy algorithm is not doing, because it's so deterministic. Remember, we talked about this when we introduced greedy algorithm. That it gives you immediately a deterministic policy. And since it's deterministic, it's not exploring anything. So the first thing one would like to do is to change this and have something slightly non-deterministic that will go around, take a chance, take a shot. Okay, I was lucky here, but let me still try that. Or I was unlucky here, but let me try it again. Okay, so this is why we need something. Okay, I will have to. Is this clear what this is the most important thing. This conceptually is the most important thing. Once you agree with this problem and this formulation, the rest will follow easily. Right? Nothing else is difficult after that. Okay, so let's see. So what's the solution? The solution is probably to explore. So what one does is one says, okay, I will be only epsilon greedy. What does that mean? I take a small number, epsilon. That's what mathematicians say. Everything small is epsilon. Right? Pick a small number. Whenever you see epsilon, it's a small number. Paul Yirdosh used to call little children epsilon. So you pick a small number and you say, for 1 minus epsilon times, I will do what I think is the best, greediest information I have. So I know some information. According to my information, action A is the best action, and I can take it. But I'm not going to take it every time. Right? So I'm going to flip a coin, and with probability 1 minus epsilon, I will take the greediest action, the best action that I know of. And in the other epsilon times, with the probability of epsilon, I'm going to take all the actions with equal probability. Uniformly choose one at random, which includes the greedy action. Okay? So this gives you a simple non-deterministic policy, which is called the epsilon greedy policy. And it has a very simple formulation. It says, the probability of given the state, you choose the action A with the probability defined on the right-hand side. So this formulation should be clear by now. This is how you define a non-deterministic probability. A non-deterministic probability should be what? A non-deterministic policy is what? It is a distribution over the actions given a state. Okay? So it's a probability distribution on the set of actions given a state. With some probability, I will do this action. With some probability, I will do the other action. With some probability, I will do the other action, given the state I am in. So this is just telling you what is the probability of carrying out an action given the state you are in. Is that clear? So you will. The reason to do this is that if you become deterministic, you don't explore and you don't get information that you did not have. So you need a non-deterministic probability. And you cannot just take any non-deterministic policy, right? So you need to make an improvement. What you need is that this should have the ability to improve when you apply this to the Q function. So this is a theorem which is actually rather cute computation. I haven't included it. Maybe I'll do it. So the theorem is stated there. It says that when I have an epsilon greedy policy, then if I try to improve it using this policy, then I get a strictly better policy pi prime. So you do this, you are going to get an improvement. So maybe I'll do the math and that will become clear. I think I did not include it in a slide. Should have included it. So currently I'm following policy pi. So suppose you're currently following policy pi. Okay, so you end up having some estimate for Q pi. Okay, so you've estimated some value of Q pi. And now I want to make a new policy pi prime. A given S, right? Which will be, suppose whatever there are m number of plus 1 minus epsilon, then A belongs to A equals the argmax. So whenever you have an optimal policy, you do this, and then otherwise you have done that. So this is your new distribution. Right? This is your new. What does this take as an input? It takes as an input your from your current policy. From your current policy, you put the value function, and you get a new policy. Right? This is how you get the new policy, by doing this. And the claim is so what you have done by this procedure, you have strictly improved your policy. It's a simple arithmetic calculation, to be really honest, but maybe doing it helps you understand. Maybe it's good that I didn't include it on a slide, because even I have to think how to do this. You don't remember how to do those things very easily. So let's see. So what I want to evaluate essentially is this. Always what we are given is QPy, so we will have to use QPy. And now I want to evaluate what happens if I put the new policy here. Right? What should that give me? That should give me so this function, if you remember the definition of this, how you did the evaluation. So if I take this action, then you will get basically this as a result. Now I know the formula for what QPy is, what this pi prime is, so I can write this as epsilon over m I'm sorry, sometimes is it allowed to sing when you're getting recorded on streaming? Maybe a different way. Right, so I have done nothing. I've just basically expanded this thing. But this is the trick. This is the standard trick. So that means that for one guy, I'm multiplying this by 1 minus epsilon. So for the special one, which is the maximum, say, I'm multiplying this by 1 minus epsilon. For everybody else, I'm multiplying by 0. What's one more way of writing 0? For the rest of them, for everybody else, one way of writing 0 is that. Right? But if I had done that for the biggest guy, for the one which has highest probability, where is the formula going here? If I remove epsilon by m out of the largest one, I'm left with 1 minus epsilon, right? So if I want to make this 1, I can just divide it by So this trick is a very common trick, converting zeros into a different formula. This is just saying for all the a's which were not maximum, I'm multiplying here by 0. The only contribution will be from the maximum guy, where the contribution will be 1 minus epsilon. Right? And plus, so this is of course an estimate. I will explain this why. Right? So once you rewrite this, now it's possible to take this sum, and you'll get this epsilon. Here you have epsilon by m in positive. Here you have, after you cancel these things, epsilon by m in negative. What you're left with is just and which is the same thing as okay. So what we have shown is that this action state function, probabilistic action state function, is bigger than the value with pi of the state. And we have done this proof before in the iteration, that once you have this information, the old proof from the dynamical system, you can check it, will imply. So given that is bigger than that, you can prove the same argument as before says phi prime is bigger than phi. Okay? So of course this might look strange or whatever, but it is so simple-minded. In probability, you often do such arguments, and I wanted to show you one such argument, where you're just replacing 0 by 0. Okay? A different way of writing 0. All right. So this is saying that our epsilon greedy policy is not a bad choice. If you apply it, you are guaranteed to at least get better. So whenever you end up, you will end up hopefully at a convergent result. So this is the reason of explaining this, that it's not like you randomly chose this epsilon greedy non-deterministic policy and there is no hope in life. Right? This actually does do the improvement. Okay, good. So I'm going to remove this and we can continue. Where is it? Any questions so far? All right, so actually I don't know. Where is my lens? Oh, okay, I'm defining Glee here. All right, so this brings us to the question of what kind of policies are good, what kind of non-deterministic policies are good, and what kind of non-deterministic policies are not going to be useful. So we saw one example, the epsilon greedy policy, right? But in general, you can have various ways of doing this. And a policy is called Glee, which is whatever it means, right? It is greedy at infinity, right? It's greedy at infinity, but explores while it's not greedy. Okay, so two things happen in this policy. Every state in action is visited infinitely many times. Why is that necessary? It says every state in action is visited infinitely many times. Because what you're trying to do, you're trying to compute Q pi, the action state function. And how did we say that when we took the Monte Carlo average, we will in the limit get the value function? What was the logic behind it? Any memory? Some of you had actually given me the logical answer then. So, law of large numbers required you for the process to converge to the actual value, you needed to be able to use the law of large numbers. So if I want to have a policy and apply law of large numbers, what should I guarantee? To be able to apply law of large numbers, you have to guarantee that each state action pair is visited infinitely often. Okay, this is the simple logic of having the first condition in the definition of Glee. And the second condition is rather simple, that when you take this average, you're getting what the greedy object would produce in the next stage. Let's say it corresponds to the greedy when you take the limit, when you take this exploration parameter to infinity. Okay, so it should be greedy in the limit, and it should explore enough so that you can apply the law of large numbers. If these two things are satisfied, you call it a Glee policy. So your epsilon greedy policy is an example of this, when you let epsilon converge to 0. So, okay. Yeah, cool. All right, so now once we have these two things figured out, the rest is simple. Now this is putting all the things. So this is the first algorithm, first complete algorithm where you can solve uh, uh, a reinforcement learning problem model-free, right? So this is the Monte Carlo Glee algorithm. So what you need, so this is using the epsilon greedy policy. What you do is you sample episode. So in each episode, when you sample the kth episode, right, you increment all the states that you have visited in the kth episode, their value in the kth cycle, right? And then you compute the Q function exactly as you computed the value function uh, in the Monte Carlo process. Your Glee guarantees that something like that will converge to the true value. And the next step, you want to change the epsilon to 1 over k. And now, whatever policy you started with, you take the epsilon greedy policy with this epsilon. So after every episode, you compute the value function, the Q value function, and you update your policy using an epsilon greedy algorithm with epsilon equal to 1 over k. In the next step, you again compute the value function for the new pi, right? But the amazing thing is you don't have to keep track of pi. You only have to keep track of q in some sense, right? So you can always recover pi time using q. Okay. So this is the first complete algorithm. It tells you that you can explore and yeah, basically that's what you do. This implements both valuation and improvement. So when you do valuation, then improvement, and valuation, and then improvement, and you have large numbers on your side, then you have the that is the Glee Monte Carlo will converge to the optimal value function. So if you remember, the optimal action value function is the goal. Once you have the optimal action value function, you can recover the optimal policy. The optimal policy can be recovered just by this process, how you recover the epsilon greedy policy from Q. Just take the greedy policy for the epsilon, take the greedy policy for the optimal Q function, and that's the optimal policy. Okay, so this is good enough to solve the problem. The Glee algorithm converges by law of large numbers to this. Good. As simple as that. Right, so this is our first completely working algorithm in reinforcement learning. All right. So before moving on, let's have a pause and maybe you should think for a second. Anything that's interests you, bothers you, excites you, drives you crazy? It's all very simple or all too complicated. It's very simple. I'm sure you'll soon get used to it. Anyhow, but we should take a pause before we move on. Okay. So there are these lectures by David Silver, and there is this book that is in the reference. They both cover a lot of variations on this, and I'm not going to cover the variations because I think once you understand one basic example, one basic algorithm, all the variations are then depend whether you want to implement it in this situation, that situation, and that's not what we are focusing here. So, but this is the main variation. This is the essential crux of almost all these algorithms, all the Monte Carlo algorithms. Okay, and so we now go to the next one, which is, so we had two ways of policy evaluation. One was the Monte Carlo, and the other was the temporal difference, the TD way. And now we'll talk about the same thing if we had done the policy evaluation with the TT algorithm. Okay. So as you had said, so now there is a phrase up there, it's called on policy. On policy, I have not defined what on policy is, but when I define off policy, what on policy is. On policy is learning by your own experience, right? Which is not something that you do in real life. You learn from other people's experience. Okay, and so this is like, of course, this is an reinforcement learning agent that's on its own and trying to learn things on its own, and it has the choice of doing these updates using some sort of a temporal way of doing updates. Okay, and that is a choice it has. And it will try to compute the Q function using now the temporal update. Okay, so you start with, and so how do you do that? So usually when we were in the action, when we did not have the action, when we just had the state, maybe I should draw. Maybe I should draw this. Drawing this is better. We'll come back to the slide in a second. So when we were interested in computing the value function with respect to pi at the state as, so we had the temporal difference algorithm. What it says is you start with your state as, you apply your policy, right? So you take some whatever pi as, let's just say it's deterministic, and you get it as prime, and you get a reward R. So usually people say p plus 1, p plus 1. And you said that you have this, you will update it to its old value plus some alpha times this is how we updated. This is how we updated the value function by saying, okay, if I had taken the policy action according to our policy, I seem to be getting this kind of a value for the value function. This is my approximation. This is my guess. So this is my error. This is what one calls the TD error. So when I take one step, one action according to my policy, I seem to be getting this error compared to my original value, so I will update it up to a factor alpha, modify this to this error, right? So this is how we did just when we had the value function. Remember that? Now what we were looking for now is not this, but we are looking for qpi. So for qpi, I need a state and an action. So what do? Is I start with the state as, I take the action A. Well, I could be in many states, but let's just keep a simple picture. You're in state S prime. Then you apply your policy. At this stage, you apply a policy. So you apply pi. So you take an action A prime according to your policy. According to your policy. Okay? And you get into the state S prime. And you have some reward. Okay? So this experience is not included. This experience is not included in your policy. This has nothing to do with your policy. This has the bit that has everything to do with your policy. So this has two steps. Oh, sorry. I get to rewrite here, I suppose. So what is happening here is you have a state, then an action, then a reward, then an action, then a state. Oh, sorry. I have to add this state. State, action, reward, state, action. That's the creativity of the name you see. Okay. And what does this mean? It means that you can have a formula just like that for qpi, which is actually on the slide. So I'm not going to write it on the board. I'm just going to show it to you. And this explains to you the second algorithm that we are interested in. Okay. So in this way of doing things, as I said, for improvement part of our cycle, starting from policy, you have to evaluate the Q function. So you evaluate the Q function, but to evaluate the Q function, you don't just need to jump one state and action, but you need to do a SARSA process. State, action, reward, state, action. So that's what you do, and you do an update. So I think it's written there. I don't have to talk exactly what it says there because I cannot read it. And then then once you get your Q, new Q, you immediately apply the new Q to get a new policy pipeline. So this is your whole algorithm. This is very simple-minded. But when something is so simple-minded, there is a small caveat, small question. And what should be the question? Am I legally allowed to do this? What can go wrong? So the previous one I kind of tried to explain, although I didn't give a formal proof, that if you do in some sense believe in law of large numbers, the previous algorithm certainly converges to the optimal value. What makes me so sure that this will get anywhere and not spit out a gibberish at the end of the day? Is there any reason to believe that? So this is the theorem that I'm going to talk about. So by the way, so next lecture will be so I'm not even explaining this right now. I'm going to take a minute to advertise the next lecture. The next lecture will be about how to prove something like that. And this will involve the mathematics of the stochastic approximation theory, which is used in many places in machine learning. So if you know even the stochastic gradient descent, it requires more or less similar mathematics. If you're familiar with the EM algorithm, it requires pretty much similar mathematics. So I think this is a good place to actually do some detailed mathematics. So that is what we'll do next time. So this theorem will be proved. Okay, but let's now, for the time being, understand what it is saying. Okay, so what we want is that algorithm that we had before actually converges somewhere. Okay, so you want algorithm to converge, and it does converge to the optimal solution as you want, as long as you have two conditions satisfied. At every step, you choose a GLE policy. You could just always choose an epsilon greedy policy. Okay, so that is your first choice. And the second, this was a question last time. I think somebody asked last time, and I said you will see the role of alphas, how you choose alpha next time. The second thing is the steps with which you update your error, the error updating steps. They have to satisfy what's called Robbins-Monroe condition from stochastic approximation theory. So Robbins-Monroe condition says that the sum of the numbers should be infinite, but sum of their squares should be finite. Do you know any such sequence? Do you know some sequence of numbers an whose sum is infinite, but sum of their squares is finite?
1 over k.
1 over k. Any number, a or k, alpha or k. That's a standard one. That's pretty much what's used in practice. There you can come up with more, right? But that's the one that people. But the official thing is that this condition is what you need to make the things work. And I have heard, but I have never seen. To be really honest, I've heard that people have used crazier alpha t's, alpha k's, or whatever. I leave it to you. If you find somewhere, tell me as well, because I don't really. But yeah, standard example is 1 over k. So it does not require the craziest numbers. So if you don't like this condition, in practice, you should think, okay, when I'm doing this algorithm, I should chase, just like in Monte Carlo algorithm, I should make this alpha t's 1 over k. That's it. For all practical purposes, forget about the Robbins-Monroe condition and do that. But if you want to understand why this algorithm or the stochastic gradient method or any such algorithm work, you should spend some time understanding the stochastic approximation theorem. So that is what we'll do next time. Okay. So I don't want to insert this in the middle of this lecture because it will be too confusing then. But now we have, so as I promised, now we have two full-fledged algorithms at least that we can go on to think about implementing to real problems. So now I will put a list of problems, mostly from this book that I mentioned, that you could try as projects. Perfectly fine with me. And of course, I will put what I want you to be able to do with that. Okay. So these are perfectly fine algorithms. Two we have already know. And the third one is more interesting, is what, by the way, I have to say, I don't know any of your names anyways. What's your name? You said learning by experience, other people's experience. Me. Okay. So I will try to remember in a minute. So this is what off policy means in this language. So off policy means that you have two policies, one that you can observe and one you want to improve. Right? This is what you said. You see somebody else, they're living their life with their policy. You're living your life with your policy. Right? And now you want to improve your policy by looking at their experience. Okay? So the jargon is, there is a target policy, the policy that you want to improve. So you want to compute Q pi and V pi for the policy pi, which is the target policy. Okay? And then there is the behavioral policy. The behavioral policy is the policy that you can observe. Right? This is the policy with which actions are actually being taken. It's the other person who's you're looking over their shoulders, as the jargon is. So this is the policy mu in this notation. So what you want is, I don't know if this page already contains the algorithm. Where is my? I cannot really tell. Okay, maybe this doesn't. So when you consider an episode or a sequence of events that you can observe, state, action, reward, state, action, that depends on policy mu. That depends on what the other person is doing. Right? But what do you want to calculate? Do you want to calculate Q mu? No, you want to calculate Q pi. That is the whole trick here. So one advantage is, of course, that when you're sampling, right, you sample, so in the Monte Carlo thing, so I think it's clear this much, but let me see why, let me explain why one is interested in this. So all right, so so we suppose to Monte Carlo, right? Or even in TD or even TD, does not matter. So what we did is we started with pi and we sampled S0, A0, R1, S1, A1, R2 to some terminal state, ST. Right? So we took a sample of this episode. Each of these actions depended on your original policy pi. Now you update it, right? So now you define pi prime equals epsilon greedy pi. So Q pi. Okay, so now you updated new thing. Now to evaluate this guy, what will be needed? You might need you will now need to create a new sequence with pi prime. Or even just for the TD case, where you just take state action reward, state action. So you just take SARSA for, let's just say SARSA. So if you just take SARSA, you have taken the SARSA relative to pi. You updated it, you got pi prime, but this data you still have, this sample you still have. And you might want to use this information over to improve your pi prime. Right? So the amount of observations that you can make in the universe are limited or costly or whatever, then you certainly want to learn about pi prime, about the value of pi prime, just from the observations that you got for pi. That is a very practical reason to think about this. Okay, and so of course you want to keep improving things, but you might not always want to be able to. And this is exactly what you were saying. What were you saying? You said, okay, there is some other guy who has had this experience, and now I have to improve my experience. Can I use this data? Right? And the next algorithm that I'm going to only mention, and maybe we'll think about also looking at convergence of this, although I haven't yet planned that part, is the Q-learning algorithm. So this algorithm is really something that works quite well for most. So far, by the way, we are only talking about, so I haven't talked much about implementation, but in all the things I'm considering, it's sort of a table lookup kind of situation. You have a table of, say, states or actions or state values or action values where you can look up it, do the experience, and update these values. And table lookup works when you have small number of states and small number of actions. So all these algorithms, as of now, as of how we are presenting it now, they are meant for small problems. It's not so easy to maintain tables if you have millions of states. Like in any practical situation, in a game of chess, there can be millions of states, right? But if you look at the game of blackjack, there are somewhere around, I don't know, 200 states, which is not that bad. 200 is still hard, but it's doable. So again, so this is still, we are still, when we are finished with the theory, we'll go back to go from a tabular version to some sort of a real data science and neural network version. But let's just continue with this. And so in this case, we have sampled. How do we do this? Okay, so we have a target policy and a behavioral policy, right? So your data is generated by your behavioral policy that produces the next AT from where you compute the value. But from the policy that you want to learn from the same state, you compute an, and I don't know what the word is actually, some sort of an auxiliary action. An auxiliary action, which sometimes one has to look up, right? I don't know. Oh, they call it just alternate. So doesn't matter. I thought there was a name for the action produced by the policy you want to learn. So by the policy you want to learn, you produce an action, and this is the one that you use in this formula. Well, you can see where I use, but I should have probably modeled it separately. So in this update, you're using to learn the value, you're using somewhere the value of A prime. You're pretending that you're learning from A prime. Right? So this is a very weird algorithm. And again, the question is, why does this converge? So this is a SARSA where you're confusing the action produced by one policy and the action producing by another policy in the update. That's about it. Okay, but strangely it works, and the question is, why does it work? So maybe we'll cover that as well next time. As of now, I think these are algorithms that will keep at this level before we go to the next level, before we go to the policy estimation level. So I will put up a set of problems for you to consider. And yeah, I think I'm going to stop here today, a little bit earlier. All right?